Yes, resistivity. First of all, what are all the factors affecting the resistivity? What are the things this resistivity depend on? Resistivity means we know that it will oppose the, it is a property of material, electrical material, which will oppose the flow of the charge. That is the basic thing. Okay. And in which way we can alter this property of the base electrical material? How can we alter it? Or is there any facility to make it change? That means reducing that resistivity or increasing that resistivity. So first of all, the flow of the charge in electrical material will be depend on the free charge first. That means free electrons present in the material. This is one factor. And second factor is the structure of the material, because if the road is not clear, that means if road is not smooth, the vehicle won't go. In a similar way, electron can be sent easily or can be flown easily if you have smooth material or if you have smooth path. So structure of material will be an important factor while deciding the property of that material in terms of resistivity. And again, is there anything more? And which will affect the free electrons again? The first property or the first thing which we have considered for the affecting of the resistivity is free electrons. So free electrons can be altered by temperature. So temperature can be taken and another factor which is responsible for supplying or providing additional energy. This temperature will provide additional energy and it may be responsible for releasing of free electrons. Okay, releasing of free electrons again alter the resistivity. So temperature indirectly is responsible for the change in resistivity of the material. One by one we will do. Next, structure of the material. The structure of the material can be defined or in terms of atoms, because material is atoms. It's a formation of atoms or it's a collection of atoms. That's why we will see the atomic structure of the material. So atomic structure is important. Atomic structure. And atomic structures are like BCC, body centered cubic, like diamond structure. And in this way we will have face centered cubic, and in this way we will have many structures. Suppose if you have any material, electrical material or electrical conductor in this way, while flowing into the material or when a free charge is going to flow in this material, it may collide with the structure. We will see in detail about that. Suppose I have a body and if I have material like this, material structure, atomic structure is like this, and there may be somehow difficulty in going in this way. But if you have another material in this, something like this, the structure of the material, structure of the atom is in this way, so it will be very free for this second case. The first case somehow difficult, in the second case it will be some more easy. So structure of the material is another criteria which will be responsible for the change in resistivity. So in order to improve the resistivity or in order to decrease the resistivity, we can change this structure first. If you change the structure, if you alter the structure, you can alter resistivity, right? So simply what can we say? Resistivity can be changed or resistivity can be altered. Resistivity can be altered by changing structure of the atom. How can we change the structure of the atom? Suppose if I have a base material A, this is electrical material. If I add another material B, which is combination of A and B, this is the material which is combination of A and B. So in this case, in the first material, I have some resistivity. Due to the adding of this B material, there is a mixture of A and B. So there will be change in structure. I have got a hybridized structure here. Hybridized structure. So due to this hybridized structure, there will be change in resistivity. Okay. So the process more or less is called alloying. This is called alloying. Now we will define formally. Alloying is a process of mixing an impurity, simply we can call it as an impurity, or a foreign material to base metal or base material to change or to alter the resistivity of the or something up to this will be open. Okay, alloying is a process of mixing an foreign material to base material is the definition for alloying. But in our special case, why we are alloying? To alter the resistivity of the material. This is our special case. Basic alloying means adding a foreign material to base material. Okay. And what is the example for this? We can consider copper plus zinc. Here copper is the base electrical material. This is base electrical material. This is foreign material. Zinc is foreign material. Okay. Due to adding of these things, it will become brass. Okay. Combination of these things. And brass will have a resistivity which is different from copper. This is the process of alloying, and we will see more detail in the next slide. Suppose basically the pure metals like copper, aluminium, they will possess conductivity, high conductivity. Okay, high sigma. That means they will possess low resistivity. Okay. If we want to increase the resistivity, we have to add to these base metals or base materials, we have to add some impurity to increase, or this will become high resistivity or some moderate resistivity. Say this is rho naught, this is rho 1. So rho 1 will be greater than rho naught in this case. So the influence of various impurities on the resistivity of the conductor depends on the metals they contaminate. Okay? The influence of various impurities on the resistivity on the rho of the conductors. Electrical material is conductor. So on the resistivity of the conductor depends on the metals they contaminate, or the materials, or the foreign bodies. We can define in any way. The metals are foreign bodies or impurities. They contaminate. Or they mix. Okay. Now, alloyed materials. Alloyed materials means after mixing of foreign bodies, they will become alloyed materials. Alloyed materials may have high mechanical strength. This is mechanical property, and something like high resistivity, or they may have high conductivity also. In some cases we need some more conductivity, low resistivity, that means. Okay. In this way they may have different properties. And the effect of metal impurity on the resistivity of a given material depend on the nature of the alloy. Of course, it depends on the nature of the foreign body it is going to affect it. So there will be basically three types of alloys formed. Okay. One is mechanical mixture alloy. Mechanical mixture alloy. And second one is solid solution alloy. Third one is chemically combined alloy. Chemically combined alloy. Okay. We will see a small discussion on these three types, because we are not specialized study about these alloying. We will see a short discussion. First one is mechanical mixture alloy. Okay. Mechanical mixture alloy. What is our alloying process? We will have one base conducting material. Okay, this is base, and we will have another foreign body. Okay, this is, say, something like impurity, and this will result in a alloyed material. When we call this as mechanical mixture alloy, if A and B have A and B have structures, atomic structure, right? And these atomic structure can be regarded as atomic volume also, okay? Atomic volumes. They are differ from each other. They are differ from each other by more than 15%. That means VA difference with VB, that means this VA and VB is volumes, is greater than 15%, then the alloying of these two materials is called as mechanical mixture alloy, where VA and VB are volumes of A and B. Okay. If the difference in volumes of both A and B is greater than 15%, that will be called as mechanical mixture alloy. And what if it is less than 15%? That is second case. Okay, that is solid solution alloy. Solid solution alloy. If the volumes are differed with less than 15%, then that is called solid solution alloy. Examples for this: copper, nickel, copper nickel alloy. Okay. And if you want to discuss more about this, what is exactly meaning? For suppose if A have something volume like this, okay, and B will have the same structure but slightly something like, we can draw in this way, slightly slanged. That means it is paralleloploid. Okay, these two things are looking like similar, but the difference in volume is less than 15%. Said it is B and it is A. If both are mixed, the mixture will be something like this. So they can be combined. More or less they will be looking like similarly. This type of mixing is called solid solution alloy. What about in previous case? Previous case is something more than 15%. So there will be a recognizable amount of change in solid structure. So due to that, we will get change in resistivity of the material. And next, we will have the third type. We will have the third one, that is chemically combined alloy. If the metals or materials A and B are chemically combined, the type of alignment is called chemically combined alloy. Example for this: zinc, manganese alloy. Okay. Now we will see some typical alloys and their resistivity changes with respect to the percentage of the impurity. First one is aluminum zinc alloy. Okay, very easy. Suppose this is resistivity and this is percentage of impurity. Okay, as the percentage of impurity increases, there will be change in resistivity. That means the resistivity will be increased like this. So what will happen to the conductivity? In the same case, the conductivity will be definitely reduced. As the resistivity increased, that will be reduced. This is percentage of impurity and this is conductivity. Okay, if you combine both these things, that will become like, if I want to draw in the same graph, this will be conductivity, this will be resistivity. Okay, next, the second one, that is copper nickel alloy. This is also, it will be resistivity and it is percentage of impurity. This is in zigzag manner. First it will increase and then it will decrease up to certain amount of time and then it will have some up and downs, some disturbances, and the conductivity will be reciprocal of resistivity. So starting it will be like somewhere here, and as resistivity increases, conductivity will decreases, and something it will be like this. This is conductivity and this is resistivity. Next, zinc manganese alloy. A typical relation or a typical characteristics of impurity with respect to percentage of impurities, that will be something like, it will concave, it is a typical material which has a beautiful characteristics like this. First there will be increase in resistivity and then decrease in resistivity after certain amount of impurity. It is a special characteristic. Okay, now we will discuss effect of temperature. Effect of temperature. What happened if we apply some temperature or if you apply some heat energy? As we already discussed, we know that for a typical atom, there will be center, and around that center we will have some orbits. Okay, and in those orbits electrons will be revolved around the nucleus. Okay, something like this. If we supply a certain amount of energy in the form of heat, radiation or light, etc., if we apply energy in any form, it may get a sufficient amount of energy from this, and that means if it is equal to ionization potential of this particular electron present in valence shell, it will be definitely free. Okay, so due to this energy, if suppose in our special case, if I apply temperature here, okay, what will happen? There will be release of electron. So release of electron means this implies what will the effect of this electron? There will be change in free electrons. Change in free electrons. Okay. Change in free electrons means there will be increase in electrons. Okay, that means increase in Q. We will see in the next lecture what is the consequence of this increase in Q in various type of materials. Okay. First, I will consider the first case will be conductors. Okay. Conductors will be most probably metals. As we already characterized, those will be almost all metals, right? Okay, in metals what will happen in the conductors due to the temperature, due to the increase in temperature, that means applying temperature means increase in temperature, what will happen? Increase in free electrons. Due to the increase in free electrons, what will happen? In conductors there will be already many electrons. Metals conductors means I can represent it in the form of more electrons, free charge in a particular body. And if there is a tremendous amount of increase in charge, what will happen to this? Suppose I have a material like this. Okay, I have already a more number of charge here. Okay, if I increase in temperature, what will happen? There will be more electrons due to what? Due to the change in temperature. And if I apply some voltage to this one, what will happen? There will be flow of current. So it won't have a free space in the conductor to flow freely. That means there will be traffic jam. Traffic jam for flow of charge. So there will be reduction in charge flow due to this traffic jam, and due to the traffic jam what will happen? Reduction in flow of charge, flow of Q. Reduction in flow of Q means what will happen? Reduction in current. Voltage is constant. Voltage is constant in this case, but there will be reduction in current. And what happen if there is reduction in current? What will happen? Voltage is constant, I is decreased. We know that resistance equal to V by I. It is constant and there is reduction in current. Reduction in current means there must be increase in resistance due to this, because voltage is constant. So there will be increase in resistance. That means due to the increase in temperature in conductors, that means in metals, okay, there will be increase in resistance, right? This increase in resistance means R equal to rho L by A, and rho equal to RA by L. Area is constant, material area won't change if you increase the temperature, and length is constant. Then Due to the increase in R, what will happen in this case? Due to the increase in R, there is increase in resistivity. Okay? Due to the increase in resistance, there will be increase in resistivity. So, as a result, due to the increase in temperature, it will result in flow of Q. It will result in increase in I. Due to this, there will be increase in resistance. Due to this, there will be increase in resistivity. So, what is the result here? Result is as temperature increases, rho will increase. That means resistivity will increase in what? In metals or in conductors. So, shall we have a characteristic relation regarding this? If I want to draw a graph between these things, a relation between these things, so this is the temperature, and this is the resistivity. So as temperature increases, what will happen? There will be at the start, okay, let me assume at 0 degree temperature, as it is conductor, there will be some free electrons, there will be some resistivity. So it will be somewhere around here. Okay, as temperature increases, it will go up to this value somewhere. So there will be increase in resistivity. So if I calculated the slope of this one, what is the slope of this one? Slope is tan theta. Okay, and if I have somewhere around here, if I measure a theta here, okay, if I want to measure theta here, what will be this one? It is a first quadrant. In trigonometry, for first quadrant, x is positive and y is positive. Tan theta is opposite side is y-axis, adjacent side is x-axis. So y-axis will be positive and x-axis will be positive. So tan theta will be positive. What is the tan theta? Tan theta is slope. So slope is positive. Okay, as the slope is positive, which slope it is? It is resistivity. Resistivity with respect to what? With the resistivity with respect to temperature. So as a result, I can say conductors will have, metals will have positive temperature coefficient. Okay, positive temperature coefficient of resistivity. This can be applicable equally to resistance also. We can say metals will have positive temperature coefficient of resistance or positive temperature coefficient of resistivity also. Okay, as area and length are constant in this case. Now we will see the temperature effect in the case of the second type of materials, that is semiconductors. Okay, as we know that as temperature increases, what will happen? There will be increase in free electrons, and in the case of semiconductor material, we will have free electrons. That means some free electrons only, one or two. Okay, and Due to the applying of temperature in this case, what will happen? Previously, say there will be some two electrons, and due to the increase in temperature, there will be increase in charge, and those will come something like this. So as I apply some voltage around this, so there will be what happened? There will be a increase in Q. Due to this, there will be increase in I. There is no traffic jam. Okay, no traffic. That's why increase in I, and V is constant. So what is R? R equal to V by I. V is constant and I increases. Due to this, there will be decrease in R. So there will be decrease in R. R decreased, so there will be reduced in resistivity. There will be reduction in resistivity of the material. So due to the increase in temperature, there will be increase in charge, and due to this there will be increase in I, and due to this there will be increase in resistance, and due to this there will be increase or sorry there will be decrease in resistivity. Due to this there will be decrease in resistivity of the material. So there is reduction in resistivity due to increase in temperature in semiconductors. Okay, so this is the result in this thing. Now if you want to draw a graph, a relation or a characteristic relation between resistivity and temperature, we can give that. Starting, the resistivity will be somewhere around here at 0 degrees Kelvin, and as temperature increases, there will be, or starting it will be somewhere here, not here, there will be reduction in resistivity. So what is the angle or what is the slope? Slope is tan theta. Okay, and if I want to measure tan theta, theta is the angle made with x-axis. Okay, and opposite side is y, adjacent side is x. So tan theta equal to y by x. And what is y there? It is fourth quadrant. Okay, in fourth quadrant y is negative and x is positive. Okay, y is negative and x is positive. So minus negative by positive, this will become tan theta is negative. So it is negative slope. And we can say that semiconductors will have negative temperature coefficient of resistivity, or we can say in resistance also. This is well applicable for both resistivity and resistance. Okay, and we will see what happens in the case of alloys. In the case of alloys, the third one is temperature effect in alloys. Temperature effect in alloys. simply there won't be a remarkable change. There won't be a remarkable change in resistivity when temperature is increased. Why? There is hybrid combination in these alloys. A will have some resistive property and B will have some more resistive property. But in this case, the resistivity is increased due to the adding of the foreign body in the most of the cases. What will happen if we increase the temperature? There will be increase in one material. It is very simple to understand. Whenever temperature increased, in a special case, let us assume there will be increase in resistivity in A and there will be decrease in B and both will be balanced. So there won't be a remarkable change. There may be a small change, but there won't be a remarkable change. Okay, remarkable change won't be there. Fine. I hope you understand this. So now we understand that due to the change in temperature, that means due to the increase in temperature or decrease in temperature, that means due to the change in temperature, what will happen? There will be change in resistivity. So due to this, what will happen? There will be change in resistance. Okay. So due to the change in temperature, there will be change in resistance. Due to the change in temperature, there will be change in resistance. So how much change will be there per unit temperature change or per unit resistance? That means, for suppose, if you draw a characteristic relation between a resistance and the change in temperature. Okay, there will be, for suppose, let me assume a characteristic curve is something like this. Okay, and originally the resistance is at R0, and for suppose if I want to measure what is the change, what is this change, if I zoom into this one, that will be like this. So what is this? Say this is R1 and this is R2 and this is T1, this will be T2, T0 originally. Okay, and temperature at T0, the resistance is R0, at T1 the resistance is R1, at T2 the resistance is R2. And what is this change in resistance? That means change in resistance due to change in temperature. Okay, this will be the change in resistance delta R, and this will be the change in temperature delta T. So how much change is there delta R per unit temperature, or something like change in resistance per temperature? How much resistance is changing with respect to temperature, and how much change per original resistance R0? I want to know this and this in a single entity. That means I want to define an entity which will give me the change in resistance with respect to original resistance per unit temperature change. That means I want change in resistance per original resistance per unit temperature. I want an entity to define a property of a material that is called temperature coefficient alpha naught. That will give me, due to these two things, which will result in this equation. Okay, I need a temperature coefficient. Coefficient is a relation. It will give a relation between change in resistance with respect to original resistance R naught per unit temperature T. So formally we can define the temperature coefficient something like this. The temperature coefficient of resistance of a material may be defined as the change in resistance per ohm per original resistance per unit degree centigrade change in per unit change in simply per unit change in temperature. Okay, and that can be written as alpha equal to change in resistance due to original resistance with respect to original resistance per unit degree temperature. Okay, that is the formula. What is delta R now? Change in resistance can be expressed like R T minus R naught, or we will define in next slide, or else I think it need a dedicated discussion. For suppose we will have a resistance R naught at T naught and resistance RT at T. Okay, and change in resistance is RT minus R naught, and that's it. The change in temperature is T minus T naught, and this will result in alpha naught equal to the change in R naught T, that equal to R minus R naught and R naught T. What will be the units? This can be expressed in ohms, and this can be expressed in ohms degree centigrade divided by, okay, ohm will get cancelled, and the units for alpha ohm will be, what will be there? 1 by degree centigrade, and that is called per degree centigrade. That can be expressed as per degree centigrade like this, or per degree centigrade. These are the units for temperature coefficient of that material. And from this relation, what can we make it? Delta R equal to alpha naught R naught T. Okay, and delta R equal to RT minus R naught, that equal to alpha naught R naught T, and RT equal to R naught plus alpha naught R naught T, and that can be written as RT equal to R naught is taken outside 1 plus alpha naught T. This is the relation to find temperature at, resistance at temperature T. This is the equation. We can write it at the top of the slide as RT equal to R naught into 1 plus alpha naught T. A valid relation to find a temperature at, to find resistance at temperature T. Okay. Now, what are the things we have discussed till now? Summary. Okay. What is the resistance? Of course, we know what is resistance is equal to rho L by A. And what is resistivity? Resistivity is a property of material which is responsible for resisting the flow of the charge. Okay. Flow of the charge will be resisted by resistivity. And what is conductivity? It is reciprocal of resistivity, which is responsible for allowing of the free charge throughout the conductor. And what are all the factors affecting the resistivity of the material? It is a free charge or something like alloying of charge, alloying of materials, and temperature effect. These in turn will affect the resistance. As affecting the resistivity, resistance will also be affected due to the alloying of the conductors and temperature effect. These are the things discussed in this lecture.